Hi, my name is Kasia Wyczesany, and I'm currently a postdoc at Tel Aviv University, hosted by Professor Shiri Arnstein-Avidan. I've recently finished my PhD at the University of Cambridge, where I worked under the supervision of Professor Tim Gowers. In this short video, I will try to briefly explain the most recent progress we made with Tim Gowers on answering a question of Vitaly Milman. That is, I will tell you about a counterexample to a strengthening of that question. I hope you won't mind that I will jump right into recalling some definitions. And the first one is the Banach-Mazur distance. So given two normed spaces, x and y, the Banach-Mazur distance between them is defined as the infimum over number c, such that there exists an invertible linear map T from x to y, such that the image of x under T in y has norm bounded below by the norm of x in x and from above by c times that norm for every x in x. When mentioning the Banach-Mazur distance, a famous Dvoretsky theorem always comes to mind. So not to disappoint, here it is. It states that there exists a number n, depending on k and epsilon, such that every normed space of dimension at least n admits a k-dimensional subspace whose Banach-Mazur distance to the Euclidean L2 space of appropriate dimension, of course, is at most 1 plus epsilon. And we will call such subspaces almost Euclidean. This is a section of the unit ball of x is almost ellipsoidal. If the section is almost spherical, that is, there exists some lambda, such that the norm of x is bounded below by lambda times the L2 norm of x and from above by 1 plus epsilon times lambda times the norm for every x in the subspace, then we will call such a subspace strongly almost Euclidean. And I'll come back to this definition. A different property of a subspace is that of being well complemented, and it describes how the subspace sits within the space. So we will say that the subspace E is well complemented if there exists a bounded linear projection from x onto E, or more quantitatively, if it is C complemented, if there exists a projection onto E whose operator norm is at most C. And there are several open problems regarding the complemented subspaces, but today the main focus will be, of course, the question of Vitaly Milman, which reads as follows. For fixed constants, k, epsilon, and c, does there exist n such that every normed space of dimension at least n, which is C Euclidean, it is a strong assumption, but it is needed, admits a subspace which is both 1 plus epsilon Euclidean and 1 plus epsilon complemented? This question turns out to be actually quite difficult, and therefore we've considered a strengthening of it. And here it comes. We are asking whether there exists always a subspace which is strongly 1 plus epsilon Euclidean and strongly 1 plus epsilon complemented. To recall, we want the section to be almost spherical, and we want I didn't mention that on the previous slide. The strongly 1 plus epsilon complemented means that there exists an orthogonal projection whose operator norm is at most 1 plus epsilon. Okay. This reformulation, this strengthening, is particularly useful because of the reformulation that we've identified. It will be, we'll need the following definition of an epsilon good point to do that. We'll say that the point x is epsilon good if for all y we have this inequality. To see what this means geometrically, let me write what a orthogonal projection of y onto the one-dimensional subspace spanned by x is, right? This is it. So now if we require this projection to have the operator norm at most 1 plus epsilon, we'll get exactly what's required in this definition. And the beauty of it is that it tells us that epsilon good points are always lying in subspaces that are both strongly well complemented and strongly almost Euclidean. We have the following lemma. You don't have to read it, of course. It states essentially that a subspace which is, we have a subspace which is strongly 1 plus epsilon complemented and strongly 1 plus epsilon Euclidean if and only if all the points in it are delta good. And there is some dependence between epsilon and delta, but it's not very important right now. So with this definition and this characterization, we can, of course, reformulate Milman's question, the strong Milman's question, to ask whether every normed space of large enough dimension contains a subspace whose all points are epsilon good. So sadly, our main theorem is that the answer is no, and that there exists a C-Euclidean subspace that contains no two-dimensional subspace, which contains only epsilon good points. And nicely enough, at least, it is quite a simple example. So here it comes. It is a sum of a randomly rotated ellipsoidal norm and a multiple of L1 norm. So let's have a little closer look. The first part uses the n by n matrix A, which is a sum of an identity matrix and a random orthogonal projection of rank n over 2. And it is root over 2 strongly Euclidean. There's also, of course, one Euclidean. And that could be, one would be unhappy about this if considering the original question. But the point here is that this norm has very few epsilon good points. They need to be around the eigenspaces. But we do have other examples of norms that have few epsilon good points. And incorporating them is actually an ongoing project. But this norm was chosen by us in the first go because it's very nice, it's differentiable, and it's quite easy to analyze. Okay. So let me also note that if eta is small enough, so it's say less than 2 minus square root of 2, then this norm is 2 Euclidean. Okay. Okay. So now, in few words, I will try to tell you a little bit about the proof. So it turns out that it is convenient to talk about support functionals when talking about epsilon good points, so we can characterize them this way. I will say that the support functional of a norm at x is any non-zero linear functional f, such that for every y with norm less than the norm of x, we have that f of y is less than f of x. So this is a little bit different than to what most of you might be used to. We will consider all multiples of support functionals. Okay. Next proposition, and don't be scared, though you don't have to read it. It states essentially that a point x is epsilon good if and only if there is some y close to it, such that its support functional is very close to y itself. Okay, so coming back to our norm, we have that its support functionals at x are multiples of functions of this form. This is the subgradient of our norm, and I'm saying subgradient because L1, of course, isn't differentiable everywhere. So we have to say that the sign takes a coordinate of x to 1 if it was positive, to -1 if it was negative, and the 0 coordinates are being taken to any element of the interval -1, 1. So that's how we deal with this non-differentiability issue. Okay. So the previous proposition tells us that vector x in our norm is epsilon good if and only if there exists some vector y and a scalar lambda, which is this multiplicity of the support functional, such that x is close to y and y is close to a multiple of its support functional. I will use this convenient notation, meaning that this approximately up to delta equal to. And let me note that this dependence on epsilon and delta is hidden in this proposition that I showed you 2 slides ago, but it's not very important. So now let me recall what A was. A was a sum of identity and the projection. So writing Q to be identity minus P, we can rewrite this approximation as to emphasize what the sign vectors must do. We'll have that the multiple of a sign vector needs to be very close to a sum of a multiple of py and a multiple of qy. So what happens here is the following. If W was a 2-dimensional subspace which consisted entirely of epsilon good points, then for every such an x, we would have to have y, which is close to x, of course, and whose sign vector needs to be close to the subspace spanned by P, W, and QW, which means this is at most 4-dimensional subspace. This will be quite difficult. Further, we'll use the statements like that. Every epsilon good point must be close to Px or Qx. This is something I've already mentioned. That means that epsilon good points must be close to the eigenspaces of the ellipsoidal mode. Further, with high probability, every point which will be close to those subspaces, since they are random, must have coordinates that take several different values, first of all, and second of all, they have to have large support. And finally, we run an argument saying that the sign vectors in a two-dimensional space cannot be approximately contained in a four-dimensional subspace. For this, we consider three cases, depending on the geometry of the given two-dimensional subspace, but that leads us to a contradiction, and that's more or less how the proof goes. Thank you very much for your attention. If you're interested about more details, you can find them in my thesis. This is not quite yet published material, but if you want to, you can find it there. Thank you very much.